A potato battery can produce voltage, and this voltage induces current flow. You can see different levels of voltage in power distribution. What is the meaning of this commonly used term in physics and engineering? In this video, we will take a conceptual journey, starting from the concept of voltage to creating a practical voltage-producing cell at the end. To understand the concept of voltage, we have to first understand the concept of electric potential. The term electric potential was coined by George Green. However, Michael Faraday made use of this concept long before Mr. Green named it. Electrical potential is a kind of energy. Let's look at an example to clarify this concept. Consider a steel ball with some positive charges on its surface. Now, let's find out the electric potential at some point near the ball. Electric potential at any point is the energy required to bring a unit test charge from the infinity to that point. The charged steel ball produces an electric field around it, as shown. The strength of this electric field is quite high near to the ball and becomes negligible as we move far away from it. Let's assume the test charge is positive. Now, let's start moving this charge from infinitely far away to our point of concern. At first, the test charge experiences very low repulsive force, so the work required at the beginning is also low. As it nears our point, the work required also increases. To ascertain the total work, we have to add all these work values together. Then, if you divide the total work value with the value of charge, you will get electric potential at the point. The interesting thing is that the value of the total work will not vary, even if you take a different path to reach the same point. This consistency means that the electric potential value is not dependent upon the path on which you take the test charge. The most important use of the electric potential concept is that by using it, you can predict in which direction an electric current will flow. The current flows from higher electric potential to lower. The Ohm's law even connects the value of current using this simple relationship. To clarify even more, let's consider one more example. Consider these two spheres. One is highly positively charged and the other is moderately positively charged. Below the moderately charged sphere, let's keep a highly charged plate. The question is, if we connect these two spheres using a conductor, in which direction will the current flow? To solve this question, we have to find out the electric potential of points A and B. Even though sphere A is moderately charged, due to the presence of the charged plate, point A will be at higher potential than point B. This difference in potential means that if you can connect points A and B together, the current will flow from point A to point B. This flow will continue until both the points reach the same potential. In this example, we see that difference in the electric potential is the most crucial factor. This quantity, in short, is known as voltage. However, this accumulation of charges is not the most practical way to generate voltage. The easiest and most practical way to create voltage is by making use of two dissimilar metals. We call such a power source a cell. Voltage produced by a cell is known as EMF. You can see that even this simple potato cell acts as a source of electricity. It produces a definite EMF across itself. Let's understand the basis of voltage production using two dissimilar metals, zinc and copper. Zinc always wants to lose two electrons and remain a zinc ion. However, a copper ion always wants to accept electrons. Therefore, if you try to add two electrons to a zinc ion, it will oppose this process. Let's find out the electric potential values of zinc and copper ions. Two electrons infinitely far away and gradually put them back on the zinc ion. Because the zinc ion opposes the electrons, you will have to exert positive work to make them move and put them back on the zinc ion. The work you have to do is shown here. When you divide the work by the value of charge, you get the electric potential of the zinc ion. However, if you move the electrons to the copper ion, since the copper ion is happy to accept them, the work you have to do will be negative. The electric potential of a copper ion can be deduced the same way. Therefore, if we connect a zinc atom with a copper ion, a natural electron flow will occur, and we will be able to note a voltage of 1.1 volts. Both of the atoms are happy with this process. The challenge is to produce copper ions and zinc atoms in a sustainable way. Let's see how to build a practical cell based on the concepts learned so far. To produce copper ions and zinc atoms in a sustainable way, let's use copper sulfate solution and a zinc metal bar. Copper sulfate solution is composed of numerous copper ions, and the zinc metal bar obviously has a lot of zinc atoms in it. The copper ions in the solution are starving for electrons. If we connect this solution and the metal bar together, obviously the zinc atoms in the bar want to donate their electrons. But after donating, zinc becomes zinc ions. Ions cannot stay in a metal. So let's introduce another aqueous solution around the zinc metal bar, just to accommodate these zinc ions. Now the electrons flow through the circuit, generating electricity, and the copper ions receive them. The copper ions become atoms now. To accommodate these new atoms, we need a copper metal bar. This arrangement will produce a voltage and electron flow in a sustainable way. To balance charge on both sides, a salt bridge is introduced. The cell we have just created is known as a galvanic cell. We hope you had an amazing journey, starting with the concept of electric potential and ending with how to produce voltage and current flow in a sustainable way. Thank you for watching the video.